I would like to thank the organizers of this event, the ATAL ACT FDP from Christian College of Engineering and Technology, Bhilai. In particular, Dr. Gajgat has given me this opportunity to interact with you. So my topic today will be on the applications of 3D printing in aviation industry. By this time, I hope this is the second day of the program. So by this time, you should have exposed to this technology 3D printing. And my talk will be on the one of the applications that is most prominent application of this 3D printing in the aviation industry. The reasons are like we need to every time work on the sophisticated material, means the high temperature alloys, super alloys. Normally you work on this aviation applications. And before we start the aviation case studies, so let us understand a bit of this 3D printing and the capabilities, why it is quite inclined towards aviation. So of course, if you see the Waller statistics, the share of the aviation industry, the application share of 3D printing, so it is definitely top three applications. We can find the aviation industry application third or fourth place, which of course the other applications of the 3D printing, probably you may come across you have consumer products, and the consumer electronics is going to play a vital role. 3D printing applications of that area, consumer products and electronics. Of course, automobile is another industry where the 3D printing, medical, and of course the aviation. So our talk will be on the aviation side. So before we see that aviation application, so let us understand the 3D printing and 3D printing versus additive, why it is so popular in this area, and what is this 3D printing is all about, and steps and various 3D printing processes, but in a brief, but not in a depth, but it's in a brief. Let us understand the capabilities of 3D printing and why particular in aviation, and the benefits of aviation industry that it is going to get with the 3D printing integration in the aviation industry. And of course, we need to have a special materials for the aviation, means maybe for your, we can use this 3D printing in aviation, like it may be for jet engine components, or it may be for structural components, or it may be for cabin components. So you have a several scope to work with 3D printing in the aviation industry, and we will see some of the materials that that are used in aviation, and it should be done through 3D printing. So those materials and specific applications, and we'll focus on. And definitely we do have a certain challenges, the fabrication challenges of 3D printing in general, and future of this 3D printing technology. So this is what I have planned for next 1.5 hours. This is the agenda for this session. And let us quickly understand the importance of this 3D printing, otherwise also called as additive manufacturing. So where it fits, like your additive manufacturing, otherwise also called as 3D printing. So right now we are in Industry 4.0, and the Industry 4.0 is all about the cyber physical systems, digital twins, where you are trying to replicate your physical facility, how close you are replicating your physical activity into virtually, and where more on the emphasis on the customization, the mass customization of the products. So then how you're going to achieve that through Industry 4.0? Of course, you do have a certain tools here to say encompass that cyber physical systems or the mass customization or the digital twin concept. So you do certainly a certain tools like or the technologies or the tools like autonomous systems, and you do have a cloud-based computing now, and you have a system integration, and you have a simulation, and you have IoT, that is Internet of Things, and you have augmented reality, and you have a big data analytics, and you have a cyber security or the blockchain technologies. And then coming to the manufacturing scenario under the Industry 4.0, it is undoubtedly it is getting shaped into an additive nature, otherwise 3D printing. So that is the level of importance that the additive manufacturing is saying by the several say surveys. It is getting more prominent in the upcoming years, now and upcoming years also. You have a lot of projections on this technology, like it may be a 2 trillion worth of parts and end products, which we need to understand the word end products. So though this technology started with prototyping application, now it has been matured enough to produce end products, means directly you're going to use these products in your say application, means it is not a prototype, it is not a component, or it is not a model, so it is going to be a direct end usage part. So that people are much interested to invest or to adoption of this technology, like aerospace, which we are talking about right now. So one among is aerospace. Undoubtedly, this technology is going to play a major role under this Industry 4.0. And of course, you may look back at the other industrial revolutions or the previous industrial revolutions, where it was started with the first industrial revolution between 1780s to 1860s with the water or a steam power, where the mechanization was the term coined during the first industrial revolution, where the human muscle power has been replaced with the machines, and the mechanical production systems has come into picture. And slowly your steam and water power has been replaced with the electrical power, and introducing the concept of assembly lines, that is during say second industrial revolution. So that is between this 70s to 1960, and where your assembly line concept, so mass production, batch production things has come into picture. And the third industrial revolution, where the predominantly say automation, electronics, information technology, and computational technologies has come into picture. So robotics and other allied technologies as more prominent during the third industrial revolution between 1970s to 2010. And where our focus will be the Industry 4.0, and the additive manufacturing is going to be the kind of manufacturing system, so that is getting shaped into additive. So then we'll see why it is so popular under these circumstances, our additive manufacturing, the role of it in particular to aerospace industry. And before we start that, let us quickly say compare the conventional manufacturing systems versus additive manufacturing systems. So the conventional manufacturing systems, so you start with subtractive manufacturing practice like a CNC or a machining practice where you need to start with a bar stock of material which is excess than the product that you're looking at, and keep on removing the material by using various um, say various tools, and the ultimately you will be ending with the product with the huge scrap or the wastage. And during this course, even sometimes we need to design a fixture to hold the work from the bottom, and we need to look for the logistics or the supply chain to produce these components. So we need to place the order for the material, tools, and the jigs fixtures, and so on and so forth. Programming, CNC programming, say we need to so look all this. And the most important thing here is the complexity of the product. Say if your product is so simple like this, a step kind of a say structure, but it may not worry much. But if you change your design from a simple step geometry to a more free-form a coffee cup kind of a geometry, and you wish to do it in a subtractive manufacturing process, then we have to think that we need to have the block of material, a big chunk of material, and we need to look for the tools that is to deep to machine this and remove the material, and what sort of tool that it should. So we need to look for several requirement towards a tooling side, and we need to look for a minimum 3-axis control here to say accommodate this kind of a undercut. So so that is another constraint, what kind of controllers that you are going to use, whether it is a 3-axis control, 4-axis control, 5-axis control, or 3.5-axis control, or whatever. This is, you have to much worry about whenever you have an undercut like this. And we need to look for a jig or a fixture to hold from the bottom to machine this part. And you have a very sharp internal feature here, so which otherwise cannot be machined without a tool radius compensation in your CNC program, and so on and so forth. So we need to look for these constraints. So, but if you come to an additive manufacturing practice, then you may not be much worried about those constraints, say right from the wastage or the complexity of the geometry. So you can very well work. You are reducing your three-dimensional complexity into a 2.5D dimension complexity. Means you are reducing the complexity. The things here to a 1 dimension or a half a dimension has been reduced. So then you could even literally remove the wastage, or no wastage you can able to produce, or with less wastage you are able to produce your part any complex shapes. So then you are keep on adding the material here in a discretized layer based thing. You are going to add the material. So then you may come across the other manufacturing process like a formative process, where every time we need to design a mold or a say die to of the same shape of the part that you're looking at. Again, you may adopt a subtractive process to fabricate these dies, or the die inserts, or the molds that it should be produced. Again, it may rely on the subtractive manufacturing process. So then again, we need to look for those constraints which we have discussed previously. So the advantage of coming to additive, so neither a die has been made, nor a tool or a jig or a fixture has been say consider or never thought of. So just we need to keep on adding the material based on the digital design that you have. So you have much freedom here. So in terms of design freedom, in terms of say material freedom, that we will discuss in length what are the benefits that you are going to get out of this additive manufacturing and why people are looking for additive manufacturing. So, and then immediately you may get in your mind, so what could be the cost of this technology? So then, of course, if you draw the plot between the cost per part versus the number of parts, so obviously, if you increase the number of parts, in case of traditional manufacturing methods like a format 2 or a subtract 2, so you can find an exponential reduction in the cost once you increase the number of parts. But you may not expect the same trend with the additive manufacturing or 3D printing. So you can expect a linear, slightly reducing the trend, like it is a almost like a constant line, irrespective of the number of parts. So one can understand that it may not meant for the mass production. So on seeing this statistics, but okay, but now the trend has gone or shifted from the mass production to mass customization. So where mass customization is going to play a vital role in the industry 4.0. And of course, the complexity of the products is getting now a lot of attention in the recent times. So which we can see, if you have the product, something like this, which it should have a standard circular, cylindrical, and filleted kind of say features, and it might have done through machining, or it might have done through welded or done separately and joined, assembled, and ultimately you're going to get this part. That's fine. So it may be very encourageable, this sort of design for a conventional manufacturing methods, but your designer has changed the design from the conventional, ordinary, or the standard, say, analytical forms or shapes to a more bionic or a more, say, nature-inspired design. So you may get doubts, sir, why you want to change the design? This design we are comfortable. No, why you want to change the design? So of course, we need to design change is needed very much for maybe adding the more value to the product, means the functionality wise, the performance wise, we need to emphasize to improve the functionality, and even to work on the other aspects of the maybe weight aspect, or maybe shape optimization, maybe the weight optimization, or which we need to, or the most important thing here is the functional aspect. So can all three F's, that is form, function, and fitment, can all these three has been modified in the existing design? So then if that happens, so all three F's has been happened, so ultimately your design has been changed to this shape. And where your conventional manufacturing systems may have a troublesome here to, otherwise it may increase the cost, which we can expect the reverse trend once the design complexity has been, say, 4x or 5x times from the traditional design. So where we need to put much cost involved to fabricate this kind of bionic design, or a nature inspired designs, or lattice based designs. So that is where forcing to unnecessarily increasing the cost of the production in a conventional methods. So in a summary, like the our discussion is continued with the previous slides, like say the cost versus the complexity. So the cost versus complexity, just now we have discussed with the increase in complexity from 1x to 4x. So even equally your cost, the fabrication cost has been exponentially increased because of this complexity increased in the product. So it has been 4 times or 5 times with the 1x complexity, the same product. Now with it has been 5 times or 6 times increase in the cost. But where your additive manufacturing or 3D printing shines here, the cost remains same, whether the complexity has been increased to 4x or 5x times. So that is the beauty of this technology as a common sense we can understand. And is it only the benefit, cost benefit you are going to get out of the additive manufacturing process whenever you are working with the complex products? So not only that, even it will enable you to come out with a kind of the added value or the performance of the existing system. Say, I hope you are aware of this is a mold for say injection molding machine, say, which we are going to give a cooling channels, say, to say get the uniform cooling or to get reduce the cycle time, that is for solidification time and ejection time and all that cycle time. So in order to reduce that cycle time, so your additive manufacturing or 3D printing will give an opportunity to confine this cooling channel, not like a straight drilled channels through a traditional conventional manufacturing methods. So you can very well confine the the model with the channels, the cooling channels, which are confining to the shape of the product. Then that is going to add the added value to your system, or it will improve the say the performance, the cost wise, the functionality wise, the cycle time has been reduced. So because of these reasons, so your additive manufacturing or 3D printing, so you are going to get the complexity as a free of cost. Apart from that, so it is enabling to generate a new say metric shapes, or to come out with a lot of design freedom. That is the more important thing here, like which we need to even may not be able to get it done through a conventional manufacturing methods. So it will have an opportunity to increase the functional performance of the product and without any additional cost. So that is the more important thing which we need to understand. So without any additional cost, you're going to increase the performance of the existing system. So that is the capability of 3D printing. And you may get doubts, sir, can it be applicable for all the circumstances? Means, say, obviously, wherever you have much more complexity in the product, and relatively looking for less number, and obviously your 3D printing may be the right choice or the best choice. But still, if you are looking for medium complexity and medium quantity, maybe CNC may be the right choice. And if you are looking for a less complex products and good number, so then you may go with the investment costing procedure or the process to select your say method. And if you are looking medium level complexity and high quantity, and you may go with the injection molding process. But there is a bit of say collaboration or integration may also be possible. You can integrate 3D printing technology with injection molding process. So how you can make an injection molding die or the insert directly with the 3D printing technology. Just now we have discussed there is with the conformal cooling channels can also increase your the existing performance of the system. Even it could be integrated with the investment costing. So you can make any complex patterns, wax patterns for very much needed for the investment costing applications. So that's the way where you can integrate this technology. Of course, it can be integrated. You can come out with a more hybrid kind of approach to say you can have a certain advantages of 3D printing. That is in terms of form, in terms of geometry, in terms of wastage, and in terms of say a lot of design freedom, which you may be enjoying with the 3D printing rather than a CNC technology. But CNC technology definitely it have its own advantages, like a better surface finish, and you have a certain advantages also. But you can combine, you can integrate these two. Even that is a good idea. Wherever you have a complex things you can do with this, and wherever you have a sort of a surface finish, or the you are looking for relatively a medium sized components, the quantity, and then you can even as well integrate this technology with any one of these conventional manufacturing technologies. And anyway, I have another session on tooling applications where I'm going to discuss in length about this tooling and the 3D printing, how it is getting connected, that we have another separate session. But right now we'll focus on the aviation or the aerospace industry, how the 3D printing is going to play a vital role. And before we start that, let us quickly see the mantra or the principles, or you name this in any way, or maybe the unique capabilities of additive manufacturing or 3D printing over traditional or conventional manufacturing methods. So you can very well say talk about this. Say the first mantra is undoubtedly, just now we have discussed, the manufacturing complexity is a free. Just we have explained with this the product. So which otherwise it could have been a cylindrical object. This may be one of the structural member in one of the structural applications. But here the idea to change the design is to accommodate, say, much improved performance with the existing design or the traditional design. So then, because of that, it is unnecessarily leading the much expensive in a conventional manufacturing methods. But that will be easily tackled here, whether you are making a cylindrical form or whether you have derived this as a the most bionic way of designing it. So which it has been nature inspired design or more organic in the form, which it doesn't care whether you are making a cylindrical form or a free form or a most complex form. So your complexity is a free totally. That's what we are talking about. And of course, you do have the variety is free. What do you mean by that? Say I have say some 100 components, but all the 100 components are different size, different shape, different form, and all together none of the components are matching. But if you go with the traditional manufacturing methods, we need to talk about CNC. Then we need to look for a different program, different tools, different fixers, which we need to work out. And there will be a huge, say, logistics involved in fabricating this. And more or less, it is varying from one part to other part. But the biggest beauty here with the additive manufacturing, so all these components in a single setup, in a single go, it doesn't care whether you are making what kind of a form. Why? Because you are going layer by layer, and you are say not derived by these constraints in conventional manufacturing. So your mindset of your designer's mindset should be now more inculcate a kind of additive nature. Means it is quite contradicting scenario of additive and subtractive. As the name it is suggesting that it's both are contradicting. But anyway, we will try to explain that with another with some of the case studies. But the thing here is the variety is a free. Means whether you make one geometry and totally, that's what where your magic lies here. So you can the part variety is a free here. That is another mantra. or the biggest advantage, as we are talking about, the no assembly is required, means you can make say 12 components, making grouping it or making it as a single component, single part or single component, where you doesn't require any assembly at all. Maybe you can consolidate the part count, or make it as a single component. So it doesn't require making the say 20 parts, 30 parts differently, assembling it. No, it doesn't require such kind of practice. The difficulty in assembling, the manpower involved here, or the resources that you put up for assembling, and you have a separate assembly station or robots, or that depends on more automation side of your thing. But here you need not invest that much money towards this assembling it, but just you make as a single part. That's another mantra. And then you have a zero lead time. What do you mean by this? So you don't have a big supply chain or a logistics normally you discuss in a conventional manufacturing methods, but you need only the inventory, that is the digital inventory, the designs that you need, but nothing physical inventory is needed here. So, and you in the course that you could be able to say reduce your lead time, or almost it's a zero lead time manufacturing, you can say, because of these disruption in all these supply chains, or the logistics that you come across in the conventional manufacturing methods. And of course, you do have definitely unlimited design space, as sometimes your designers say imagination or the thinking should not be the hurdle for the manufacturability of that component. Like say you have your designer has come out with a nature inspired design, so which your manufacturing system should not be a hurdle for to fabricate this kind of say nature inspired design, where your designer has that out of the box thinking and then come out with the better performance than the traditional design. So can this will be say focused here? Yeah, undoubtedly you have a lot of say design say freedom, unlimited design space, which you can able to get it. And of course it is a zero skill manufacturing. What do you mean by this? So of course you do a train in a conventional tool making, or even it is a CNC technology, we need to train the people on these sophisticated say machines and programming and tool making and all that stuff. But here the magic lies in the much on the design side, rather than the manufacturer's skill is not much needed here. So if you contrast with the conventional manufacturing systems, so the magic lies maybe in the so the manufacturer skill may not be much required here, to much focus on the design aspects, and that design should in tune with the capabilities. That's what we are discussing all this. So it should at every part of your design, it should be say understood that whether you are going to exploit these unique capabilities in your design or not. And you have this technology as giving an opportunity to more compact portable manufacturing nature. So you have more compact size of these say machines, or the printers more compact in size, and you can carry these printers to your place, and it's not restricted by your casting lines or your say shop floors, where we need to have a huge equipment to, and where you need to go to that place, and then where you need to perform that. But here it have a lot of democracy in printing or fabricating or manufacturing. You can sit relax from your home also. You could able to perform your say fabrication process. So it has a lot of say freedom, or rather than democracy in manufacturing, and less wastage byproduct. So that's what where you can have say zero wastage or less wastage towards the manufacturing of these components. So that is another advantage, or literally zero wastage of the byproduct through additive, and infinite shades of the material. This is a quite interesting stuff if you contrast with the say conventional manufacturing methods. So you can even fabricate a circuitry material, non-circuitry material in a single setup, or you can vary the composition, or you can fabricate a functionally graded material which it requires a perform a different functionality at the different regions within the same component. So that is also quite interesting. So you can go with the infinite shades of the material. That is the another mantra, the unique capability of additive manufacturing rather than the conventional manufacturing methods. And now you are talking about Industry 4.0, and then how precisely your physical replication has been done with the virtual. Means you talk about the digital twin concept, or this sort of scenario of Industry 4.0. So definitely it is into a more digital digitalization of your designs, and getting say integrated with the physical world or the physical replication, and just you can integrate the even with the digitizing technologies here to the 3D printing. So you can even get wonders, or you can come out with the best outcome. So if you integrate these technologies in your manufacturing practice. So with this background, let us talk about say one say you have a sort of a manifold here. Why I'm quoting this is very much, it may be relevant to our aerospace application which we are going to discuss, or in general your mindset of the designer's mindset has to come out from the traditional design mindset. Like say, on seeing this, one can understand this is definitely meant for the conventional manufacturing. This design is definitely meant for a conventional approach, maybe a CNC, maybe. Why? Because you may be much worrying about the wastage, keeping in mind that less wastage. So you may be left out with a block kind of a the structure, rather than say a shell, or adjusting the, or scooping out the material to onto a more lighter side. So you may get doubts, sir, why I want to change my design. So I am comfortable, let it be like this. So let it be like this, it won't work. Why? Because so you have an intention to reduce the weight of the component. Why you want to reduce the weight of the component? Obviously, that matters. The application matters a lot, whether this component has been used in aero industry, or whether this component has been used in automobile industry, automobile or aero engine, or aerospace component. So then it matters a lot. So 1 gram, even you forget about 4.6 kg to 1 kg, it has been say reduced. So why you want to reduce it? Say I want to fabricate this through additive or 3D printing technology. So why unnecessarily I want to use this much material, the block of material? Why? Because my 3D printing take a lot of time to fabricate this. So, or not only that reason, like say, I want to improve the performance of the system, existing system. So it may say forced us to change the design from the traditional or the direct part. Has been, say, if you just replace the manufacturing method from the subtract to the additive with the same design, if you want to proceed with the direct replacement, so nothing is going to get out of this 3D printing technology. You're not going to get benefit out of this. So just we discussed some of the 10 mantra. So can it be realized in your product? So then definitely we need to undergo a design change here. Predominantly the interior, but sometimes it may be the exterior form can also be changed. But in this case, where I am changing the block-based design to a shell-based or more into the form has been changed without changing the functionality, or without say changing the fitment of the product. So I have an opportunity here to change only the form. Yes, you can change only the form without touching onto the other two F's. So that is the functionality and fitment. So you will be focusing only on the say form. Then obviously you can change the form. And as for your additive manufacturing and 3D printing, you have changed the design, and where you could able to save 4.6 kg to 1 kg and 78% weight reduction. And it may not worthy, or which you are not improving any functionality to the product. Let it happen once again you further adapt, or further you say use a design for additive manufacturing approach. Means you are now changing the functionality of the system, the manifold, that you are getting an improved fluid flow within that, and the fitment or the compactness has been improved. The space now, you have saved a lot of space, or the fitment of it. So altogether you have changed the all three F's. So that is, you have changed the form, and you have changed the uh, functionality, and you have changed the fitment. So all three F's has been changed. And in that course, and even you could able to reduce the weight to 0.4 kg and 91% weight savings, and with the improved functionality and the improved fitment of the product, and less space is needed, and the easier assembly, all that, the 10 mantra we have discussed, definitely you're going to get with this design. So this what where design is not the goal, the fabrication is the goal. Then how do you get fabricated in a more effective way? So then you have changed the design accordingly, and with keeping in mind that increasing the functionality, or at least the retaining the functionality or better functionality. So you are targeting and then getting done to this approach. So that's what where your 3D printing is shining. And in continuation with that discussion, like say you have, instead of a solid block design, you have made as a shell rather than a solid block. So then with this change, with this design approach, so your 191 hours has been reduced to 36 hours because of the shell based. And further you have applied certain, consider your support structure, and consider your orientation and other aspects. So that is the constraints in AM also you are considered, and accordingly you have modified the design, and further your the build time has been reduced. So means your machine say cost per hour has been reduced, means your production cost has been reduced, and material is also reduced, means your material cost is also reduced, and totally your production cost or the product cost has been reduced huge. Because of this, you are exploiting your capabilities, unique capabilities of additive manufacturing in redesigning your product. So from the conventional mindset to the additive mindset, which you could even get these benefits, right? And now, what is this 3D printing? We can quickly see that. I hope you might have already exposed this technology. This technology has started with prototyping with the name, and then you have the additive manufacturing, and you have a 3D printing. So given by the ASTM or Cherry Wallers or whoever. So the idea is same. You start with the digital data and end with the physical product, or the physical say component. So then use it for your application. Either you come from the CAD/CAM CAE domain, or the digitizing domain, or a medical domain, a CT MRI scan also can be done. But the essence remains same. Like you start with the digital data and end with the physical component, and then you are going to get the benefits out of this technology. So of course, you may come across the different steps. Typically, you may have 8 steps that we need to follow in any typical additive manufacturing and 3D printing process. We need to start with the CAD model, and it should be getting converted into a STL, that is a a stereolithography or a standard tessellation language, which we need to your printer means the interfacing software which is connected with your machine can understand only this format, and you import that STL file to interfacing software, and you set up the machine setup or the build setup has been based on the process parameters that you set, whether it is a laser driven system, you set the laser related parameters. If not, the software will automatically suggest some default parameters. So then you set all the parameters and it will automatically generate your setup or your commands that has been sent to the machine. So within that machine, your physical realization of your part has been taken place here, and remove the part from the platform, or you might have given some supports during this ease of fabrication. You remove that and do a post processing here to enhance the physical or the mechanical properties that you are not satisfied as built the machine. But even further you can do, or you remove the supports or loose powder, or depends on the type of AM process that you're using it. So it will vary your post-processing method. So ultimately, once you have done your post-processing onto this part and say your application is ready, so let it be a simple application like sipping a coffee through a coffee cup, or even it could be a jet engine component, so that it is fabricated through this additive manufacturing process. So let it come the form or the complexity anywhere it's going to take up, and it is getting fabricated as for your requirement or the application which it demands. So it could be a sort of jet engine aircraft component. So, but you may get doubt, sir, can it be used directly as a jet engine aircraft component? Yeah, you do have a certain, say, the certification and the qualification of these parts, so that has been already proven by the ISO or ASTM, along with the Federal Aviation Authority. If you're talking about the aviation application, yes, it has been already got certified along with the users like maybe GE, maybe Pat Whitney, maybe Airbus or Boeing. So their products has been certified by the Federal Aviation Authority or any other regulator who gives the certification for your aero engine components, or for that matter. So you have a lot of scope, so that has been further tapped this in the sectors like aviation, but people have been doing it, but still further it should be much industrialized or much adopted technology. So than now, means that still you can see something in my words saying that some sort of hesitation or some sort of it has been not come to a plateau of productivity. If you put it in a more a Gartner cycle or a more expected cycle, but still it has to be adopted by these industries or industrialization. But you come across several challenges. Like once you're seeing only the one side of the coin, but if you come to the other side of the coin, you have several challenges that it should be addressed. You have that also we are going to discuss. So in general, like which we need to even go with an additive manufacturing of these components. So definitely, which we need to understand these constraints of some of the constraints which otherwise you never talk about these constraints in a conventional machining practice. Like say you're talking about some support structure or the orientation, the part orientation, fixing or selection of the part orientation, or you do have a certain constraints. What is the minimum feature that you're going to get out of this technology, and what sort of material that it's going to able to process? So, or can it be the same for a reactive material or a non-reactive material? Can it be processed the same way, or high temperature alloys, or it should be. So now we are talking about all our high-end applications, but definitely you have the material is going to play a vital role here, apart from the design, the geometric optimization, or the material optimization, or your design optimization as such, in tune with the additive the mindset, or which we are going to exploit that anyway. So with this background, so let us go to so coming to the classification. I hope maybe other speakers may be talking about, covering about all these same processes, but I'm not going to talk about all these processes. But ASTM and ISO with 5290015, so they have standardized this say 3D printing process into 7 groups. So you have a binder jetting, directed energy, material extrusion, material jetting, powder bed fusion, sheet lamination, VAT photopolymerization process. But don't call this technology with the other names. These are the proprietary names, but they have standardized into a more terminology, which is a more generic terminology, rather than biasing to any one of these vendors. So normally they develop this technology, are having a patents on these technologies like FDM, SLM, SLS, or DLP, SLA, or EPM. These are more into a proprietary names or commercial names, but they have standardized by keeping into a 7 categories of this AM or 3D printing processes. But the lot of material freedom in one of the magics or the mantra which we had discussed, multi-structured, functionally graded, or varying composition in your product. Or you can even use a natural materials, maybe a functional material or a natural material, maybe a biological cell, or a blood cell, or a living cell from the patient has been collected and it has been used as one of the materials. So more natural material, food grade material, or electronic material, shape memory material, apart from your standard engineering materials like polymers, thermoset, thermoplastics, metal alloys, ceramics, and composites. And apart from this, you have the added advantage, which you can even go with your tailor-made material. And the form, normally the feedstock form, either it could be a powder form, a filament form, or a sheet laminate, or a liquid form. So normally you come across these feedstock material, and not much going in depth, like just an overview, understand like how your polymers are getting printed through additive manufacturing practice in a single step. Why I'm calling this as a single step? So directly you can produce polymer, or can all the, you can see like all 7 processes as per the ASTM standards. All these 7 processes can capable of producing polymer in a single step, means direct say processing, or in a single step, without further say giving to the secondary process like say any other infiltration, or further improving the properties. But definitely you can get it done through a single step polymer processing with all the 7 AM processes. And the type of material just as a polymer, and the state of fusion, either it is a thermal bonding or a chemical reaction bonding. Or then how do you say get this feedstock form, maybe a filament form, melted material, powder form, liquid, or a liquid material, a sheet form? Or how do you deposit, or how do you distribute this feedstock? The distribution method, maybe through a nozzle, through a print head, or through a powder bed, or again this is through a liquid, through a print head, or your powder can also be in a print head, or can it be a VAT based, or can it be a sheet based? And the basic principle involved, either it could be an extrusion process, or jetting, multiple jetting of the material printers, or the selectively fusing the powder particles from the powder bed, or you're jetting the binder from the print heads onto the powder form in case of a binder jetting system. Or even it could be a light reactive photo material which it is getting cured so by exposing it through the say light source. Or even it could be a fusion of the stacked layers So that is in sheet lamination. So you have different principles here and supporting the 7 processes. So this is a single step polymer processing, or even you can go with the metal also in a single step, but you cannot process all the 7 categories here with a single metal. Maybe hardly you can go with the 4 processes among 7 to go with the single step. So that is either again a melted state or a solid plus melted state, or a solid state fusion may happen, or then feedstock may be a filament wire or a powder or a sheet material, or the distribution can be done through a nozzle or a powder or a stack or a laminates. And the principle may be selectively deposition of the material onto to a substrate, or selectively fusion of the material in a powder bed, or the fusion of the sheets, stacking of the sheets. And the source of fusion may be, you may use electron beam as energy source, or a laser predominantly, or you can use an inductive heating, and that is with this principle, or you do use an electron beam again or a laser to selectively fuse the material, the powder bed. Selectively you are sintering it or melting it through a laser or electron beam, or even you use an ultrasound. Maybe some solid state welding can also be used. Sonotrode can also be used to say join these or laminates, and finally you're going to get your part that's a metal, which is quite straightforward and single step. But even it could be done through a multiple steps, means the initial steps remain same, but you are going to get only the green part here, and then further it should be subjecting to a furnace sintering or a infiltration. It completes the 100% metal or a composite or a ceramic, but not in a single step. You should every time undergo and secondary process, the furnace treatment or infiltration. We need to, that is a mandatory to get your 100% physical properties of your metal, composite or ceramic, whatever it is. Then it is quite possible, but with the multiple steps it is possible. And then coming to the applications of this 3D printing, so we can see the major share goes towards the consumer products and the consumer electronics, that is around 21.8%. So, and second place goes to a motor vehicle. A motor vehicle means that is automotive, automobile together, it is 18.6%. And third may be a medical, dental together 16.4%. And the aerospace industry may be around 10.2%. So where right now we will be focusing in this sector, the aerospace industry. And you do have industrial business machines also, means in that case it may goes to the 1, 2, 3, 4, maybe fifth share. But this may vary from 1 year to other year. So this I picked from a whole statistics. This is a bit older, maybe 3-4 years back, but definitely we can see a lot of improvements in aerospace in the recent times. Why? Because a lot of adoption by the these aero manufacturers. They are say adopting several metal, especially metal 3D printing technologies. They are acquiring, like GE has acquired a Morris technology to produce these aero engine components. So you have a lot of potential to further say tap here in the aerospace industry. And of course, you do have other applications like academic institutions, like the AICT has taken a right move to even the what you call your central syllabus, like nowadays your CBSE is also imposing to integrate the 3D printing technology as a part of their regular school level education, or +1, +2. So then you have a lot of potential. That is an increasing say sector, that is academic institutions has been adopting this for either teaching purpose or maybe research purpose. So then people are increasing this area, the academic institutions, government, military, architecture, and other applications. So then if you see the hype cycle or a Gartner, that is the expectations versus time. So you have a say to come with the plateau of productivity. So you have the 3D printing service bureaus and 3D printing creation softwares, and enterprise 3D printing is almost now coming, touching without no time. So or with less time, maybe within 2 years, it's getting touched here, the plateau of productivity. But you have to a long way to go certain applications. So you have aerospace and defense applications here right now, the 3D printed aerospace and defense applications. So this is almost like coming to this trough stage, but it should come to the plateau of productivity. Means it has to go at least 5 to 10 years of time to reach this application, the aero and defense application come to this stage. But that's what I'm agitating. But still, it has been started here, and then it is coming slowly, and then it may be reaching here maybe after 10 years down the lane, then it should be. And you may see other aerospace applications, even it may be here and there, which it may be taking a long time to touch here. But the initial applications like prototyping and other medical applications, and now it has been almost within the less time, maybe 2 to 5 years. So these one may touch here. But definitely the aerospace, which it will take a long time to get the certifications, maybe the other reason, so which we need to talk about. But anyway, so you have the certainly a good amount of time that should reach the aerospace and defense 3D printed components to be productivity or more industrialization or more adoption, so that it may take. And if you see the sort of the growth, this is the 3D printed parts. So the market size in million euros versus the industry. So from this is the predicted, or even if you see right now we are here, so 2021, so where you have the predominant application is aerospace is bit low here, definitely. So you have aero industry is a very limited industry, right? But that's the thing where you can understand. But let's say where you have the medical industry, you have right up to this, and you have an automobile industry, and then followed by electronics, and which you can see the consumer products. So which you can see there is a drastic growth of this over the period of time, maybe down the lane. But aerospace is not much increasing, so it's slow and steady. It is having the reasons are several, right? So anyway, so and then coming to the level of say whether what purpose that you are using it. So still the prototyping application, which you can see. So you have the prototyping application, and you have the molds tooling application. This is going phenomenal. And of course the production parts. So this is quite interesting. The production parts, or there is a huge demand to the coming years. The production parts are getting increased, that trend if you see. So that is the indication how this technology is maturing, right? Say, though it started with the prototyping applications and then tooling applications, and now this is the turn where the production parts are the end usage direct parts has been a lot of say growth in the future. So that will tell you the story about this technology. So for the down the lane, maybe next 10 years or 20 years, so the growth will predicted in this way. So that's what where the people are looking for this technology. And if you see, you do have a lot of variety in the products. Like you have a low end products, like say, which you can sit, relax in your home, and you can be able to print some domestic parts, or that is right from your bedroom itself. You can be able to print this. Or further, you have the desktop based printers, which is of much faster than the filament based one. So where you have a technology called say clip, or that is promoted by the Carbon 3D. Then this is much faster. So it may be 10 times, 15 times faster than the extrusion based or filament based technology, which we can see there is a huge say developments are happening, even in terms of say low end 3D printers to high end 3D printers. So you have the industrial printers, so the used for the industrial applications. So right from the domestic applications to the industrial applications, you have a lot of developments in terms of the application of this technology, maybe in aerospace, maybe in automobile, maybe in medicine, or everywhere where you have the much into a bigger size components or the technology like DED or wire or additive manufacturing systems, which even entire fuselage of an aircraft can also be done through these machines. So that is what where this technology is shifting. Even you have the huge growth. So it is not so ignored the growth in the desktop based or a low end machines to the high end machines. So it is happening, the growth is happening everywhere from the low end to the high end 3D printers in the recent times. And which, can you believe that this is a 3D printer? So that has been printed and then material changeover, and it has been integrated to the a robot. So definitely you have a lot of say developments are happening in this direction. You have more degrees of freedom. Right now, the 3D printing or additive manufacturing technology is more based on the 3-axis control, but now you have the more access and you can produce any curved say structures. So that is very much needed for aerospace industry, where you have a lot of aerofoil shapes. So either it could be an automobile or aerospace, which it should be further. I will try to play the video. Where it should be further, which you can see. Can you believe that this has been 3D printed part, this much big sized part through 3D printing? I'll try to play this video also, you can get better understanding.
For nearly 3 decades, Stratasys has led the way in additive manufacturing, from the prototype labs to the production floor. Stratasys is unveiling 2 phenomenal new technologies. One which is a 3-dimensional infinite build, which allows us to start building parts out of the box in a much faster way.
It enables products to be made that are much larger and potentially of unlimited length.
It opens up opportunities for large-scale fixtures and some of the large parts that we have. In the midterm, I think that the materials development side has a lot of opportunity, especially in looking at automotive relevant materials that meet all of the requirements that automotive applications may need.
So we've accomplished this by flipping our traditional FDM technology on its side and combining it with a tool changing capability. This has allowed us to achieve speeds of 10x plus from what we know of FDM today. We're producing parts that are now measured in feet versus inches.
We look forward to a large ecosystem which offers large production, stability of processes, and a robust base of design, materials, and structures.
In the longer term, we're concentrating on more designing for the function of the parts, so that we could potentially have better function for those parts.
And the second technology allows us to use a robot to get into areas in a 3 or a 5-axis way that's never been done before.
It's a very exciting time for additive manufacturing, and Siemens working closely with Stratasys on the robotic composite 3D demonstrator.
With this project, we bring the strengths of Siemens and CNC and CNC-controlled robots with the strengths of Stratasys and FDM, and we elevate it by adding our CAD, CAM, and simulation tools so that we produce a truly unique platform.
So like this, we can produce even bigger structures from this. Either it may be an automobile or even an aircraft for fuselages can also be done through. And let us come to the typical applications where we'll be concentrating on the aerospace applications, but you have a lot of potential in the consumer electronics, consumer products, and even automobile industry just now we have seen, and the medical, where you need to have a lot of customization of your dental bridges, copings, crowns. And aerospace, as we understood that we need to have a more lightweighted structures and more complex geometries that you come across, and that is very much done through additive manufacturing. So that's what where your aerospace industry is adopting this technology. And you do have other tooling, molding industry to use this 3D printing technology, or even other applications like military or architectural, oil, gas, and space applications, and even for the jewelry and other applications which you can find. So then coming to the aerospace, so where you are now huge life cycle saving potential from the aircraft engine. You can even see the trend in the recent times, maybe from 2003 onwards. So then the aero engine manufacturers, they are exploring from 2003 onwards to metal AM facilities to fabricate these engine components or the structural components of the cabin components. So you have a high quantity of these AM that should be done through this additive manufacturing, and it may take the performance testing of these parts and certification, and then people are on the way to get all that qualification, certification, and these components. And you have the key players that has been, say, expanding this manufacturing capabilities to come out with the new equipment and acquiring the suppliers. Like, as I already mentioned, Morris technology has been, say, the GE has been acquired that technology for producing these aero engine components. And you have a series production and manufacturing capability which needs further extended this. And you have a potential volume for the new turbine series that it should several thousands per year. So you do have say additive manufacturing is going to play here the key say AM components that is found with the multiple say engine parts, injection nozzles, or even the production of the tens to thousands of this single component per year. So that is the demand which we can find that's forcing these aero manufacturers to adopt the additive manufacturing technologies. And you have a new generation of these turbines so that is expected to be launched within the next 3 years. So the manufacturing infrastructure that needs to be established in this time. And you have the fuel nozzle example from the GE. So they're it's a great potential. So they are say lightweighting the things, and they enable the fuel consumption also, and less carbon say footprints, like the emissions, the carbon CO2 emissions also reduced. So you have a certain advantages once you come to this additive manufacturing. And with a simple example in aerospace, one can understand the importance of additive manufacturing or 3D printing in aero industry. So you have a traditional buckle design. So this is conventional steel buckle. It is weighing around 155 grams. So that is done through a conventional or a traditional design and the traditional manufacturing method. But whereas, so if you come out with an additive or 3D printing optimized design more into a topology or a lattice-based design, so your 155 grams even has been, say, if you alter the material steel to aluminum, so it may save a less saving from 155 to 120 grams. But further, you integrate this design, the optimized design and more lightweighted design. So, and with the material as a titanium, but definitely the cost is high. That can it be justifiable? Yes. So then how do you get justified? So then then only it is meaningful, like once you are adapting this technology. Otherwise, so it's simply you're replacing the steel with titanium. It is a costly thing, undoubtedly, like whether it has been added some added value to the product. So that is the most important thing here. So that's where your say titanium buckle has been designed for with your additive manufacturing, so which is of 70 grams now. So means almost like a 55% reduction in the weight. So what you're going to get out of this weight reduction, say 70 gram. So if you see 70 gram, it may be very less to you. But like say you have, if you take a typical Airbus 380, so it will be having 853 economy seats. So all these economy seats will be having this say a buckle, the seat buckle, and now you can able to save within a single aircraft. So you are able to save 72.5 kg. So that is a huge saving in terms of say fuel saving. Means say if you take a lifetime of this aircraft, so it will be saving 3.3 million liters of the fuel. Or typically, if you could able to say save 1 kg payload in your aircraft, so it is saving 45,000 liters of your fuel. So that is a lifetime. Lifetime may be typically, so it may be 15 years or 20 years lifetime of your aircraft. So which we can understand the added value, the functionality or the savings to a simple example, which will demonstrate the why the people are looking for this 3D printing technology, right? So this is a simple example to demonstrate the importance of 3D printing in aviation. And not only that, you have a certain prototyping applications for the fitment functionality and assembly testing. So where you have this engine casing and aviation, the jet gas turbine engine, you have this engine casing. So all these are done through 3D printing process. And you have a certainly unmanned aerial vehicle, which you have a smart wings, and it has been printed through 3D printing technology, and where you have been integrating your LEDs and other electronic part here. And even for the say fuselage connection with the fuselage to the say you have the wing to fuselage, you have this connection, and then these are say these prototypes or the functional things which it is getting printed through a 3D printing technology. You have a lot of composites now. It has been added to the 3D printing say processes. So you can even add those materials even for further exploiting these capabilities, or even some kind of a pilot say your dashboard can be even further optimized. Or even you can see nowadays you have these housings, the toroidal housings that has made with one of the polymer material called Altum. So there is a lightweight, strength to weight ratio is high. So this is where you can make use of this technology even for that side of a direct part production. Directly these parts will be used for your end usage. Or even it could be a satellite assembly that has been printed, these parts except electronics, everything has been printed through a 3D printing technology. Or even you have a camera, so that has been used in one of the aircraft engines, so it has been printed through additive manufacturing. And one advantage which you are going to get out of this is the part consolidation. So you have a ducting design, the traditional ducting design, so it was like 8 to 9 parts, but now it has been possible with the 3D printing as a single component. So you have a lot of part consolidation has been happened here, right? And then you can see these parts has been direct part production. Means like you use the metal 3D printers to print them in aluminum, or even an Inconel, means a nickel based superalloy can also be used here. Or you have these superalloys nowadays can be possible. So these direct parts may be in your aero applications, where it has been, even it could be a door handle, or even it could be a combustion chamber. But you imagine that if it is done through a conventional machining, there will be a 95% or 96% wastage of the material. You don't have a luxury to waste say 95% the nickel based superalloy. That is as costly say as far as the cost is concerned. So you can exploit that kind of say advantages here through additive manufacturing. So again, with the traditional design to topology optimized structures for lightweighting and improved functionality of the parts, which you can come across. Or even you can see these impellers, so that has been used in the aircraft applications, maybe blades, turbine blades, or these kind of structures or the impellers has been made through direct 3D printing metal 3D printing parts. And these imagine that it is been direct part production applications that people are using this technology. Even this is one of the very well-known case study from the General Electric, that is the fuel nozzle. So this fuel nozzle, initially it was 20 parts. Now it has been as a single part. So, and that too, it has a 19 nozzles in a single engine. So means you have two engines in an aircraft. So 19 into 2. So you have 38 nozzles that, and then it has 25% reduction in the weight. And again, just now we have discussed not only the production cost saving, but it is also saving a lot of fuel in the lifetime of this engine. So then you have a 5x durability. Then you have the durability has also increased, and the weight has been reduced, and the part count has been reduced. The more part consolidation has happened, and you have a lot of advantages once you come to this the aviation industry that is adopting or integrating 3D printing. Or even you can see these combustion chambers, so that has been printed and has been used in the aviation industry. And not only the engine components, or even it could be a structural components. So the structural components very much the bionic designs, which it is lightweighting structures where the lattice based structures, so which you can further reduce the weight of the structures and say 15% lighter than the traditional designs versus the lattice based design here. And the bionic spacer panel that has been used by the Airbus, so in their aircrafts. So you can imagine that how this 3D printing technology is say able to produce these structural components or the jet engine components. And there is one project from General Electric in aviation. They are quoting that say they started this project in 2015, and just recently they got the certification from FAA to certify these components that are used in a catalyst engine. That is 1/3 of the engine parts has been 3D printed. So the advantages, like it is a more simplified supply chain logistics versus the traditional casting or the machining practice. Normally they do adopt for fabricating these parts, but there is a huge say supply chain simplification in the product manufacturing, and assembly got simplified, and then the maintenance become very less maintenance. It has been because of this adoption of 3D printing technology. And of course, more than 10 lbs of the weight has been reduced in this say aircraft engine. So, and 10% more power and 20% fuel burning efficiency. So it has been added advantage and simplified maintenance or the operational cost. So you calculate, if you calculate all this, and you can better justify these components so across the say people, why these people are able to say use this and of course you do have aerospace rockets. So you have a monolithic thrust chambers, so which is so you have a fuel injector thrust chamber, and it has been made as a single component. And you can see because of the lattice structure, it has been adopted here. So it serves a double purpose, means it is say promoting the lightweighting of the say structure, and it is also promoting the cooling efficiency, the performance. It has improved cooling because of this lattice structure. So that is what where your aerospace industry is looking for this kind of solutions. And otherwise it should have been done through machining CNC with a great difficulty onto a nickel-based supralloy, that is Inconel 718. But it should easily now it could able to done easily here with more complex structures with more lattice or bionic designs. So it is serving the multi-purpose in the product. So that's the thing where even you have a bio-inspired or lung-inspired heat exchangers, and you have more lattice-based structures. So again, a lightweighting of the structures, and you have the more compact versus the traditional designs. So you have more compact designs and more bio-inspired, and you have, say, this aluminum or even a copper can also be processed through 3D printing. So where you have the best design in the universe. Undoubtedly, it is a nature-inspired design, and the best materials, best of the best materials in the universe that is getting now 3D printable. So you're going to get even a spiral design of 0.5 mm wall thickness. So that is very much gettable through this 3D printing. Otherwise, it may be tough or impossible through a conventional, or a lot of wastage, a lot of production cost through a conventional manufacturing methods. With a great difficulty you may get it. But why you want to invite those troubles wherever you have this kind of structures, and better you can make use of this technology and adoption of this technology. And you can see further, say you see here is a traditional design which is of more say a sort of a bulky design, or a solid design, rather than which is a traditional design. So which is of weight 5.1 kg. And if you say measure the functional surface area, so it is the functional surface area in the heat exchanger, it is 823 centimeter cube. But whereas with the 3D printed designs or nature inspired designs, more of say scooping out of this material for lightweighting, as well as the functional surface has been now almost say 11 to 12 times say higher functional surface area. Means one can imagine the performance of this system, how it has been improved with the even the weight has been reduced to 5.1 to 1.9 kg, and with the better functional surface area, almost 11 times or 12 times better functional surface area. So where one can understand the importance of this in aviation industry as such. And you have the RF antenna. So this was the previous traditional manufacturing method. They used to do a brazing medium, and it used to take 8 months to develop this part, and it consists of 100 parts in this assembly. But now it is made as a single part, and it has been done through metal 3D printing system, and a fewer weeks rather than 8 months. And now your timeline maybe not in months, maybe in weeks, you are going to compress your time. And then not only that, you are able to even 95% weight reduction in this component, and 20% reduction in the production cost, and 75% non-recurring cost has been eliminated. So like this, you can find several say case studies in this area. So the aviation in particular, and you have a structural elements. So these structural components, this is also again a lattice based say design. So where instead of using a traditional say designs, it is more on a bio inspired or a cell inspired design, where you can even say produce this kind of say fabricate these components, and which will be just now we have discussed the advantage of the lattice based designs. So where you can fabricate easily these things through 3D printing. And this is another satellite part. This was the traditional design, and through additive manufacturing, so it has been now in a titanium material. So you know the beauty of the titanium. It's a lightweighted say material, and then you can get the advantage of the even both the material advantage, the functionality, and as well as the lightweighting that is very much needed for your say satellite, or for your aircraft, aeronautics or aerospace, which it is very much needed. Then that will be achieved through this 3D printing technology. And then you may come across the topology optimized structures, and then this bionic or a lattice-based designs or the generative designs. So you may be much familiar about these design philosophies now in the recent times, though it was started with the parametric and two-dimensional sketching to the more advanced or the recent bionic lattice or a topology optimized designs or the structures. So then designing is not the goal. Then ultimately we need to fabricate that designer's imagination into a reality through 3D printing. So it is very well achievable, and it should be, say, done through this. And you do have a certain, say, tools, software tools to support this topology optimization and the bionic designs and the generative designs. But the thing here is, like, say, either it is an automobile or aerospace component. So the biggest advantage which you are going to get out of this, which we have been talking about, and the unique capabilities which we discussed right from the beginning of this 3D printing technology. So it will be further, say, exploited. And you do have a certain tools, software tools to do topology optimization like Altair OptiStract or N topology, and you have other softwares to do this job. And ultimately, it should be produced through the 3D printing, fabrication through 3D printing. And let us come to a certain fabrication challenges of this 3D printing. Say, we have a lot of scope to work on a research problem in additive. So then that will be one of the areas that is a multi-physics, multi-scale modeling is held a lot of scope. Why? Because you have a very few commercial softwares to perform this, and that may be targeting to a particular make of the machine or their own proprietary product or the machine or the material. But we need to do these simulations before you go with especially the metal 3D printing practice. Why? Because you don't have a luxury to waste or utilize these costly and more precious materials to know the costly materials. And then if you are not performed this the design has been not performed, or you are not predicted the defects in your part, then you may be ending up with a difficulty of a build failure, or maybe a defect part at the end of the day you're going to. So that may be because of several reasons, maybe the huge temperature gradient or the residual stresses inside that has been built because of the large thermal cycles, so that has been involved. Why? Because you are operating at the 1000 degrees C or 2000 degrees C to process your say superalloys, for that matter, a inconel based material that you're processing for your aerospace applications. So then, which we need to understand the distortion effect. We need to understand the residual stresses effect onto your form of the your structure, and it should suggest a kind of a compensation. Otherwise, you may end up with the distorted structure or more say warpage or a lot of shrinkage in your features. So then, which we need to do a certain optimization in the support structure, which it should be done. And then we need to minimize the damage to the recoater if it is a powder bed system and you have the recoater or a roller to spread the powder, and the location of the part is going to judge a lot. Then you need to understand that through a simulation studies, and then which we need to minimize the number of build tryouts, and even it will also predict the post-processing requirements, maybe heat treatment or hipping and other support removal and other stuff, and which it should ultimately optimize your build orientation, support configuration, and the operating conditions, like know about the residual stresses or stress concentration in your, say, structures or the products that you are fabricating, and sometimes it may damage your parts also. Then which we need to understand that, and we do have a certain simulation tools to perform this job nowadays, from even from the CAD/CAM CAE vendors. So you can find at least one tool or the software tool to do say ANSYS additive print and 3D systems. We do use a 3D expert for doing the simulation, and we have other players, other commercial softwares from Hexagon, Simufact, and even some extent Autodesk NetFab or SimCenter from Siemens. You have this simulation softwares. And then let us say come to our last part of the presentation. So then what are the advantages of this practice over the traditional manufacturing methods? So definitely through 3D printing in aerospace, you can utilize the premium materials. You don't have a luxury to waste these premium materials like Inconel or aluminum or titanium. So those are costly and the premium materials that you can have a huge cost saving once you come to this additive manufacturing or 3D printing. And you have another advantage of part consolidation. We have been talking about this. Fewer man hours required for assembly of your, you could have a lot of savings in terms of part consolidation of the structures. You could be able to do it, and you have a lot of optimization in the geometry, so that leads to a high performance of the design, so not subjecting to a traditional constraints normally you come across. So that is, you are going to balance this both the things through additive manufacturing. And you have a lightweight components which it also saves the fuel saving over the life of the project. That's what we are discussing. A simple example of a buckle, or even it could be a door handle or a buckles, which you can, that will be the same logic will be extended for your the underhood components, that is in your aero engine components or structural components or cabin components, or wherever you have the scope that you can do all that optimization. And you do come across these companies like GE, one famous example, not only this, the fuel nozzle, and SpaceX, also they are integrating the 3D printing technology in their practice. Airbus, and we can see several aero people that they are adopting this. Maybe you have the say the material aspect like titanium 64, titanium 6246, titanium 834, nickel based superalloys, and which can have the lot of say working conditions, and titanium aluminide, so which you can make use of several parts of your aero engine that it has been made through even 3D printing practice. And say you see the materials for your aero applications, like say application and the example and the requirement, and of course the recommended AM process versus the recommended material. So you have the engine compartment parts. So you can have, for example, a nozzle vessels. So that nozzle vessels, you have the requirement of a heat resistance, the functional part which we very much needed, and go with the powder bed based SLS, that is selective laser sintering process, will be used here. And you can even go with the glass filled nylon. This is a composite, so like a glass filled nylon will be used here to go with this requirement. The heat resistance and functional parts has been done through. And you have a carbon accessories in your aircraft, then go with a kind of example like a control console parts. So these control parts, the requirement is the customized functional knobs. So that is very much needed. Then you have the lot of customization capability through additive manufacturing and 3D printing. So that has been done through a VAT-based SLA system, and the used material is standard resin, the epoxy resin, to get the functionality of these knobs and more customized designs. And you have the air ducts. So these air ducts, you have the ducting, airflow ducting is example, and where the requirement is flexible ducts and bellow directs. So these directors, the bellow directs are done through a nylon material, nylon 12 through a powder bed system. And full-sized panel, the seat backs, and you have entry doors. So all these are very large sized components. So these are large parts with the smooth surface finish. So you can get the best of the best surface finish through a polymer based system, is a VAT based SLA system. You have a standard resins are being used for this panels, full size panels. And you have the casted metal parts and these brackets, for example, brackets and the door handles. So the requirement is metal parts which has been casted, so using 3D printed patterns. So here you are integrating tooling application. Here you are using the master pattern as integrating with the sand casting application here. So that is you are making a sacrificial pattern through a castable resin or a wax-based material through a VAT system or a material jetting system. So, and then you have a metal components. So you have some suspension wishbone that has been used in a jet engine, say components. And the requirements, or we need to consolidate the parts, and we need to have a light weighting of the structure, and we need to have a functional metal parts. So then go with the metal based powder bed system, and go with the material like titanium or aluminum. So then you can say get these requirements for these components. And you have some vessels, and these vessels, you have a dashboard interface where you will be using that vessels. And this is the end use custom screen vessels that is very much needed. That is the requirement. So you have very 100% transparent material. So through a digital ABS, that is then done through material jetting technology. And you have the lights. So you have the headlights prototypes. So that is fully transparent and highly detailing. So again, you go with a kind of SLA or a material jetting system. So which is a more transparent based, say, material. So you can name any component anywhere, like it could be a cabin, or it could be a electronic lighting, or it could be say underwood, or a cabin part, or a structural component. So you can find everywhere, either in terms of a prototype or a tool or a mold or a direct part. So you can find these applications in your aerospace. But certainly we have been talking about only the advantages, and definitely we need to so talk about the negative shade of this additive manufacturing or 3D printing. So coming to advantages, which we have been talking about, it has a lot of freedom for designer, and complexities are free, and potentially eliminating the tooling requirement, and lightweighting design, part consolidation, and elimination of the part steps, production steps. So, but you do have a certain dark shades of this or disadvantages, like you do have a slow build rates. So it is not as fast as you remove the material in a CNC technology, but definitely this is still a slow build rates, but it should be further has been the speed, especially the metal printing speed, should be further improved. So it is not as you compare with the traditional rate, but it is not, definitely it is not, it is on very far from that reality. And you have high production costs. Yes, so you have the equipment is costly, as well as the material powder which you are using, maybe around 25,000 rupees per kg if you are using a titanium. So then definitely you have high production costs of these products, and which is resulting your say high cost of the metal printers, metal practice. But polymer printing now, it is relatively cheap, relatively on par with the conventional processes, but still your cost in a metal printing, still it is a luxury. And considerable efforts are required to the application design and for setting the process parameters. Like this is a huge challenge for the metal 3D printing especially. So you have around 180 plus parameters to control your say quality and the process control. So it will become and it is a lengthy process, and then it is a complex process to optimize your parameters. It's a challenging one. So you may ask, sir, do you have any standards that has been followed to Yeah, you do have a few standards that also I'm going to cover at the end. So definitely, your manufacturing processes, like say, a lot of anisotropy is another a disadvantage or a drawback of these components. But this anisotropy you can manage or minimize with certain design guidelines or certain say rules, thumb rules. If you follow, you can minimize some extent this anisotropy or surface finish, dimensional accuracy, which is almost inferior to the conventional manufacturing methods. But you do enhance these things by post processing. Say you can even enhance by, but it may add some extra cost definitely. So you may use a post processing method to improve the density, for example, or to improve the that is a physical property or the mechanical property. So definitely it may increase the cost, but there is a possibility that you can do that, but it should not unnecessarily increase the cost. So your design is the where you can minimize these defects or the constraints which you talk about. So can be adjusted somewhere, some extent, right from your design adoption of which is in tuning with the 3D printing approach, not the conventional approach, which you normally, the design mindset normally you have. And discontinuous production process may be the another limitation, and limited component sizes. But it may be slowly bridging the gap, which we might have seen one of the videos which I played. So size may be still not applicable for all the AM processes, but majority are suffering from the build limitation, the build size limitations of the components. But still, at least one or two processes even could able to process, say, 3 meter by 4 meter by 4 meter is also gettable. But not all the processes can make that much size components. And do certain challenges apart from our earlier discussion. So it will be there right from the material feedstock preparation. So you have the powder, and then which whether it has been made as for the standards while preparing your feedstock powder, and then what is the powder size, the shape, the flowability, and all that into matters. Like so then we need to check right from the material feedstock preparation to design. Just now we have discussed a lot about the design aspects, and the other speakers might have touched up on these aspects. But definitely it needs to have to do a lot of tweaking here and there in the design. So, and then layout, as I already mentioned, like how best you can make use of your build chamber and versus your the feedstock distribution system. So we need to even organize how do you fix your orientation or the layout of the part that you are going to, and you need to work on the layout in a proper way. And then process parameters, of course, which you have been talking about, around 180 plus parameters, and during post processing, and ultimately your accuracy, surface quality, and material properties. So these are the outcomes. So that is going to judge your each and every phase of your say 3D printing process. Like say what are the considerations which we need to say consider. So your surface tension or your viscosity, it matters a lot. Again, that depends what kind of EM process or 3D printing technology you're using it. That will dictate we need to consider these stuff. Staircasing effect you cannot eliminate, or we can minimize at least. Then how do you do that? And volume contractions and heat dissipations, anisotropy and micro melting, all that things should be considered, and a lot of implications which we need to address here, and in such a way that it is further say industrialized, or which we are talking about the plateau of productivity that it should come, but not immediately. Definitely it has to go a long way to say adopt these technologies And then the standardization is another hurdle or the challenge. So to standardize your process or the machine to machine or run to run, there will be an inconsistency and the errors may proven. Like say, so you need to understand and say these challenges should be how do you address this, and post-processing requirements, it may unnecessarily increase the cost of production, and how do you minimize this? And this is another challenge. Maybe sometimes 60%, 70% of the cost, the total cost may going towards the post-processing cost, which is contributing around 60, 70%. But that's not say good anything to so do such kind of a thing. Then definitely there will be a challenge here. And certification of the parts, the qualification certification of the parts and new potential hazards whenever you work with the powder bed system, especially. And you have integrity of the digital designs, like say, which we need to secure our digital data. Why? Because you have a lot of digital inventory rather than a physical inventory here. So we need to have a certain blockchain technologies or your security, cyber security, or your say cyber laws may be rewritten. Maybe somebody may tamper, or somebody may pirate your designs. We don't know like how you're going to protect. Is another challenge, and IP protection is another challenge. So like this, you can keep on talking about certain fabrication challenges and some common defects which you can come across. Some balling effect because of the different surface tensions in the melt pool to the adjacent say powder, some keyholes or chemical degradation or oxidation, which we need to go with some inert environment or vacuuming it. So then you have cracks can be formed because of several reasons. Delamination with the substrate to the part or within the layers, or a lot of distortions or the shrinkage, warpage kind of stuff, inclusions and poor surface porosity. So you have several common problems or defects you can come across. So then how do you say overcome these defects? Or like so then definitely it is a kind of a challenge for you as a user. Then in a normal flow, then you can say 3D printing is just a push button game. Yes, it may be a push button game, but which we need to address these challenges. So definitely we need to work on that. So then only you are the best user of 3D printing technology in a cost-wise justification, or the added value to the product has been justified. So once you say take up all these challenges and converting them as a challenge, the opportunity, and then you do it. So that's what where you have to leverage, and right. So and you have certain ASTM ISO standards as on date around 35 to 40 has been published, and another 35 to 40 is under development. So in terms of the design for additive manufacturing, so you have a certain design, general design guidelines, and in particular to powder bed, or in particular to DED system, or in particular to functionally graded materials, you have certain design standards and material extrusion design standards, and you have certain post-processing design standards also, which we need to understand. And the feedback, the feedstock say standards like characterization of these powders, you have a certain standards, the ASTM and ISO standards for the various materials like titanium 6.4 to say ELI grade to 718 Inconel and Inconel 625 and stainless steel. So you have aluminum 10 mg. You have a different say feedstock characterization of standards, and AIM fabrication standards. You do have say test specimens or the mechanical properties of the metals, or cobalt, chrome, material specific or thermal post processing. You have a certain fabrication standards through this powder bed or a DED system with the different materials. You can have a terminology based, which we have already discussed in the previous slides. So and then what could be the future? So future, maybe you may be coming out with the several lanes, maybe 4D printing, 5D printing. So 3D printing is all about making a static structures using your materials. But whereas 4D printing is all about, you have a smart material, hydrogels or shape memory polymers. So you can have a multi-material 3D printing systems here, and inverse problem modeling, and a static structure initially you're going to fabricate. And further, it has been more dynamic, intelligent, and more smarter by applying some stimuli or some temperature, water, energy. So it is getting transformed over the period of time. So it may be a simple application like say unscrewing, screwing, or maybe a life-saving a hot stent can be also 4D printed, and it can be used in your life-saving application. So in future further, you can see a lot of scale down models, maybe micro-sized, nano-sized components can also be anticipated, and more self-healing microstructures, or more even the EVs or fuel cells can also be printed through 3D printing, or more into digital and analog structures, hybrid structures can be printed, or more into an voxel based printing. It may not be a layer based approach, so it may be a voxel based assembly. This may be the assembler which could be able to assemble millions of voxels per second, maybe the speed of this printing. So let me conclude my 2-hour lecture on, say, which we started with the introduction of 3D printing in Industry 4.0, the importance of this in Industry 4.0, and conventional versus additive manufacturing, steps involved in 3D printing process and generic applications, and which is pertaining to aviation case studies and benefits to the aviation industry, and 3D printing materials in aviation, and fabrication challenges and the future directions. So this is what, and these are some of the facilities we have at NIT Warangal for in terms of metal 3D printing, polymer printing, and then we have a dedicated softwares for 3D printing applications. So these are some of the facilities we have. And say, let me conclude my talk and handing over to the organizers. So if you are having any specific questions, and I am very much thankful to the organizers given me this opportunity, or even if you have a queries, very well you can ask me, or even you can mail me also. Otherwise, I have another session. It's over to you. That is as for the organizers time limit, then we can go accordingly. Yeah, it's over to you, sir.
Yeah. Participants, if you have any query, please ask, or you can post in the chat box also. Yes, any query?
So did you find anything in the chat box? Question?
No, sir. I think.
Yeah, even they can unmute and ask.
Yeah.
Hello.
Yes.
Yeah. So, sir, thanks for this nice session. Sir, my question is, which software is mainly we use, basically is used for that additive manufacturing process, or we can say the can we go for the simulation based, so that we can check the layer by layer manufacturing in any one of the software?
Yeah, even you can get the simulated layered view in all the softwares. Like it may be from the proprietary software which is supplied by the vendor along with the machine.
Yes.
But the major challenge here is, so in a real time, the scenario is different. So that's what which you may anticipate these defects. So that is the challenge lies here. Yeah, you can do a simulate your say laser paths, or your the nozzle paths. Depends on the type of AM process that you're using it. You can very well simulate it, but how closely you can say estimate, evaluate the defects or the errors in a real time, so it will come. So that is the major challenge here. So it may predict, but it may not be 100% accurate results which you are going to get. But still, it is a open challenge for the 3D printing community to fabricate 100% defect free or 100% say deviation free from the original CAD design to the physical 3D printed part. So again, coming to your question, simulated, it will give some extent, but not.
Yes, because in some many software we can check the subtractive manufacturing, but for the additive manufacturing,
Yes.
that it is very somewhat observed. It is complicated in the software also.
Yes, why? Because you need to work these in a more say thermal cycles, which you and a lot temperature gradients, so you can anticipate. So that is quite challenging. It is not as easy like a conventional say process which you come across. Yeah, that is a major challenge. Yeah, especially metal printing. Why? Because you are operating at the elevated temperatures, so down there 1500 degrees C or 2000 degrees C. But that's the challenge where it lies, especially metal printing is concerned.
Yeah, thank you, sir. Thank you.
Yeah, any other? I think there are more questions. Thank you, sir. Thank you very much for sparing your precious time and sharing your knowledge and experience with us. Your session was very interesting and informative. You have well explained the different aspects of 3D printing and its application in aviation industry. You have taken so much examples. I think it would be very helpful for the participants to do the research work in this area also, and it will be benefited for all the participants. Also, I would like to thank all the participants for joining and attending the whole session with patience. Thank you all again. Thank you, sir.
Yeah, thank you. Thank you for the opportunity. A nice interaction with the participants. Thank you.
Welcome.